Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is mechanical power, torque, and rotational speed. Our objective is to describe mechanical power produced by a motor and consumed by a generator in terms of the measurable quantities of torque and rotational speed. We'll develop an understanding of their relationship with one another and the units used to measure them. First and foremost of our tasks is to differentiate between the dual nature of rotating electrical machines. Motors on one hand and generators on the other. Their most basic distinction is that of direction. Both types of electrical machines can be viewed simply as energy converters. Their only difference lies in which direction that energy is converted. Motors convert electrical power into rotational mechanical power. Generators convert rotational mechanical power to electrical power. It's really that simple. Granted, there are subtle and not so subtle differences between machines exclusively designed for one task and not the other, but for the most part, these concepts applied to motors are as equally relevant to our discussion of generators. If your interest is exclusively one-sided, feel free to skip to the important parts. I wouldn't be too hasty though, because it's all important. You'll find intriguing connections between motors and generators. Long story short, motors use the magnetic field produced by electrical energy to physically rotate a shaft with a given twisting force called torque at a given rotational speed. Generators, in contrast, use moving steam, water, or wind to twist a shaft inside a magnetic field at a given speed to generate electrical power. Second of our tasks is to introduce an extremely misunderstood, at least by most individuals with a primarily electrical background, means of measuring rotational mechanical force, namely torque. Torque is expressed as a concept, appropriately enough with the letter T. We'll describe the units and derivation later, but for now, let's just talk about what torque is meant to represent, a twisting force. Force applied linearly for people of reasonable intelligence is easy to visualize. Twisting, not so much. For linear application, it's very easy to imagine pushing, pulling, or moving an object that weighs or otherwise resists you a certain amount F, be it in units of pounds force or newtons over a certain distance d, be it in units of feet or meters. At the time you stop moving the object, you sit back, crack a cold one, and say, "I've done work today." By using the term work, it means you put a certain amount of energy into a system. That energy is measurable as force times distance, which would be expressed in units of foot-pounds force or newton meters, which can be easily converted to joules, where 1 newton expressed for a distance of 1 meter is 1 joule. You'll often see the concept of energy written in shorthand using script W. I'm emphatically recommending you do not do this for two very valid reasons. One, a common unit of power, the watt, is also written shorthand as a regular W. It would be an unforgivable mistake to equate the two. Power is not energy. Energy is not power. Power is the time rate production or consumption of energy. Power is energy over time. 2. Script W is cursive. Seriously, show of hands. Who writes in cursive anymore? People that still have landlines write in cursive. People that read newspapers made out of paper write in cursive. People that wear monocles write in cursive. No one writes in cursive anymore. Why are we still teaching cursive in public schools? But I digress. If I move an object that resists me with 180 pounds of force, a distance of 9 feet, this means I've put 180 pounds force times 9 feet, or 1,620 foot-pounds force of energy into the system. Similarly, using SI metric system units, if I move an object that resists me with 800 newtons of force, a distance of 3 meters, this means I put 800 newtons times 3 meters, or 2,400 newton meters into the system. If a joule is equivalent to 1 newton of force expressed for a distance of 1 meter, this is equal to 2,400 joules of energy. Additionally, using engineering prefixes, I can write this as 2.4 kilojoules. This is pretty easy stuff, and scenarios involving linear applications of force are featured prominently in the Hydraulics and Electrical Control of Hydraulic Systems playlist that deals primarily with linear hydraulic actuators called cylinders. Now along comes a rotational actuator in the form of a motor-driven shaft that's obviously revolving at a high rate of speed, but not really going anywhere. There's some obvious force behind that spinning shaft, because if you grabbed it, it'd rip your balls right out of your sockets. But how is all this measurable, quantifiable, and somehow comparable to our previous description of mechanical energy? My recommendation is to keep thinking linearly. Imagine, if you will, a winch with a rotating shaft that has a radius r. The shaft has a magic rope hook to it. The magic rope doesn't weigh anything, nor does it have any thickness or stretch or break or give you rope burns or do any of the other things normal ropes do except pull. That rope is attached to an object that weighs or otherwise resists movement a quantity F, be it units of pounds force or newtons. Then you spin that shaft one full revolution. Aha, some of you already see where I'm going with this. Before we take this concept home, let's return to the concept of twisting. You are no doubt aware of the simple machine known as the lever. Levers make it easier to apply force because of their length. A longer lever will obviously produce more torque given the same input. Don't believe me? Take one of those big old $200 textbooks you never open, put it in one hand and hold it close to your chest. Not so hard. Now extend your arm horizontally and keep it there. A little different, huh? There's more torque because that identical force is being applied with a longer lever. This is the twisting force called torque, T, and it's obviously directly proportional to both the force applied, F, and the distance from the center of the circular arc it's trying to describe, R. For our textbook example, granted you've got gravity in there and eventually that circular path won't be so circular, but for now, think of just that brief arc where that force is torquing your arms in a completely circular path. If that same torque was applied continually along a complete circular path, it would act tangentially at every point. What does tangentially mean? It means like a stone from a sling. If we release the stone at any point, it flies tangential to the circular path and smashes through your neighbor's window. Yeah, there's a good story behind that one. Getting back to the point of torque being proportional to both the force applied and the length of the lever, we get the formula T equals F times R. Longer lever, more torque. More force, more torque. Commonly used units of torque would be foot-pounds force, inch-pound force, or newton meters. Notice the similarity of units with that of energy. Torque is not energy, it's still torque, despite the commonality in units. For those with a vector physics background, you realize that energy is a scalar quantity, one that has magnitude but no direction, and torque is a vector quantity, something with both magnitude and direction. The magnitude of torque may be the same at any given point in the circular path. However, a sling stone cast at points 180 degrees opposite of each other would cast the stone in two opposite directions, which is kind of the punchline to my sling stone through the neighbor's window story. Returning to our linear winch example, when a motor is pulling the object toward it at a constant velocity and the load is neither accelerating nor decelerating, the winch is always producing torque equal to F times R. Now, consider the work or energy put into the system when the shaft turns one revolution. From the perspective of the object, energy put into the system is force times distance, F times D, because the object representing a resistance force F moved a certain distance D. It's easy to figure out that the distance D is equal to the amount of magic rope that got wound around the shaft when you revolve the shaft one turn. The distance D is the perimeter of the shaft, where the perimeter of a circle is known to be 2 pi r. Note, D is not diameter, which is another animal entirely. D is the linear distance. If distance equals 2 pi r and energy equals force times distance, we can substitute this into our energy equation, where energy is now equal to force times 2 pi r. Knowing our earlier definition of torque as F times R, 2 pi and F can change seats on the bus and make it easier to spot a place where we can substitute torque into our energy equation. For every rotation of a shaft producing a given amount of constant torque, it delivers 2 pi T of energy in either units of joules or foot-pounds force per revolution. Ta-da! That's how torque is used to describe energy input into a system. And the magic show ain't over yet, folks. Left out of this discussion entirely is time. Suppose this shaft performs a certain number of revolutions within a given time period. This same amount of energy can be input into our system slowly or rapidly, and this time rate of energy change can be quantified. I'm of course leading up to a discussion of power. Power is not energy. Energy is not power. Power is the time rate expenditure or production of energy. Power is energy over time. In the SI metric system, a joule per second is equivalent to a watt. In the US customary system, the unit of power is the foot-pound force per second. Power is a unit of energy over a unit of time. If you want to, you can package power up into some more readable units called horsepower, where 1 horsepower is equal to 746 watts, or 550 foot-pounds force per second. If you are still hazy about the distinction between power and energy, by all means check out the Energy and Power lecture available at the Big Bad Tech channel and clarify any remaining misconceptions. If you need to perform a certain task, it requires a certain amount of labor. Let's say you've got to stack a cord of firewood. The cord of firewood represents a measurable quantity of energy you must put into the system. How fast you stack that cord of wood is your choice. If you stack that cord in 30 minutes, you accomplish the task powerfully. If you picked at the task and dragged your feet and bitched and moaned about it over the course of 8 hours, you did it not so powerfully. More powerful input allowed you to accomplish the same task quicker. Less powerful input required more time to accomplish the same task. It makes sense. Linearly, power is pretty easy to conceptualize. Take a certain weight and lift it up. If it took a short amount of time to travel a given distance, you put a lot of power into the system. If it took a long amount of time to travel the same distance, the input was not nearly as powerful. Rotational power is not as easy to conceptualize, albeit it's intrinsically much easier to understand than our earlier discussion of torque, because a rotational shaft is obviously rotating at a given speed, or number of turns per given time period. If it rotates slowly, yet is still exerting a constant amount of torque per revolution, chances are it's delivering less power to a system than one exerting the same amount of torque per revolution, but doing so at a greater rotational speed. The missing link in our discussion of power is this rotational speed quantity, which some genius decided to represent mathematically with the letter n. Rotational speed is commonly expressed in units of revolutions per minute, or its abbreviation RPM, regardless of your choice of measurement systems. Given a shaft with radius r exerts a certain constant torque T for the course of one complete revolution, delivers 2 pi T of energy per revolution, how quickly is it doing so? i.e., how powerful is it? If power is equal to energy per unit time, the answer is quite obviously power is equal to energy per revolution multiplied by revolution per unit time. Units of revolution cancel out, and you're left with energy per unit time. The only problem with this understanding is your choice of units. Given rotational speed is commonly expressed in revolutions per minute, and power is customarily expressed as watts or a joule per second, or its US customary equivalent of foot-pounds force per second, we must convert revolutions per minute to revolutions per second by converting 1 minute to 60 seconds. The final expression for mechanical power yields 2 pi T times n divided by 60. Since 2 pi and 60 are actually constants, pi being the irrational 3.1415 blah blah blah, you'll sometimes see this written as mechanical power equals torque times rotational speed in revolutions per minute divided by 9.55. There are all sorts of derivations from mechanical power given foot-pounds of torque as an input and converting to joules, or given inch-pounds of torque and converting to joules, or given newton-meters of torque and converting to foot-pounds force per second. They're all useless to you because you're not going to remember them and I'm not going to make you. The reason I'm not going to make you remember these different formulas because I'm utterly confident in your ability to convert individual units at whatever level of abstraction necessary to get the job done. Far more important than all this mathematical wizardry surrounding torque, speed, energy, and power is the application of these quantities to our first point. Most people realize the fact that motors convert electrical power to mechanical power, which thanks to our mathematical wizardry, we can now measure with some convenient and understandable units. voltage and current must come in for torque and speed to come out. What a significant percentage of people don't understand is that it takes torque to spin a generator a certain speed. It doesn't just spin with no resistance, and you're not getting electrical energy from nowhere. There's a finite amount of energy that can be extracted from a physical phenomenon like falling water, expanding steam, or blowing wind. The more electrical power you try to extract from this phenomenon, the more the generator resists you and the more torque you need to apply to rotate at a given speed. Torque and speed must come into a generator for voltage and current to come out. Like I said earlier, there are intriguing connections between motors and generators. Consider applications of a single electrical machine with a dual nature. Imagine an electric car using electrical energy to go up a hill in motor mode, yet when it goes down a hill, it switches to generator mode and slows the car down to a controllable speed, and at the same time charges the batteries. This is the basis of regenerative braking, and I find this extremely cool. Related to our discussion of power and energy is the concept of efficiency, and our previous maxim that power in always equals power out. This is not to say that a motor converts 100% of the electrical energy it is supplied into an equal and exact quantity of usable mechanical energy, but it does imply that 100% of the electrical energy it receives is converted into something else, a portion of which is usable mechanical energy, the rest being losses. Obvious losses include frictional losses from the shaft riding on bearings, and I2R losses in the motor windings because these windings have real, albeit small, measurable resistance and heat up when current passes through them. Not so obvious losses include hysteresis losses, which are magnetic losses in the iron core of the motor, and eddy current losses, which are electrical losses in the same core. Not so obvious losses, at least for those without a requisite knowledge in basic AC circuit analysis, are the reactive interchanges that can occur with some configurations of motors and generators. The very nature of all electrical machines requires an interaction of electrical current and a magnetic field, so one can expect, nay guarantee, that current will lag applied voltage for non-power factor corrected AC motor configurations. Given that voltage and current are not in phase with one another, we can expect real power actually available for conversion into usable mechanical energy to be less than what we're apparently supplying to the motor. Notice the terms I'm emphasizing: apparent, real, reactive. Some of you may be scrambling for your notes on these topics right now, but for now, just be comforted with this simplification. The real power delivered to the motor by the electrical utility should be some fraction of that power apparently supplied to it. This first hoop is known as power factor. Having cleared this hoop, the usable mechanical power produced by the motor should be some fraction of that real electrical power supplied to it. This ratio of useful mechanical output over real electrical power input is known as efficiency. And unless you found something on the internet claiming otherwise, all real-world motors and generators have efficiencies of less than 100%. Some of them are more efficient than others, but you can't get more out of something than what you put in. The same goes for education and practice. Speaking of practice, let's try a couple illustrated example problems dealing with torque, rotational speed, energy, power, and efficiency. I'm encouraging you to get involved with this lecture by pausing the lecture often, working out these illustrated example problems by yourself. Ideally, your answer should match that of the illustrated example problem. If not, the illustrated example problem is there to guide you to the correct solution. If you're like me, when you're rotating your tires, you torque your lug nuts to 2 grunts or until the wrench imprints its manufacturer's symbol into your palm. Let's say, however, your user's manual suggests you torque them to 90 foot-pounds force, and you've got 2 wrenches capable of doing the job. One has a 6-inch shaft and the other a 15-inch shaft. Which wrench will require less force to deliver the required amount of twisting force? If T equals F times R, the answer is, quite obviously, the longer wrench will require less force to deliver the same amount of torque because it's a longer lever. If we wanted to compare some hard numbers, we'd have to perform some algebraic manipulation. Solving for force, we obtain the equally valid relationship T over R equals F. The only thing stopping us from launching this rocket is a simple unit conversion. Notice the desired torque value is expressed in units of foot-pounds force. the length of our wrench is expressed in inches. We need to convert the length of these wrenches from units of inches to units of feet. The length of our first wrench is therefore 0.5 feet. The length of our second wrench is 1.25 feet. Substituting in the necessary values for the small wrench, we find we need to supply this wrench with force equivalent to the weight of a healthy 20-something dude at 180 pounds force. If, however, we use the larger wrench, we find we only need to supply this wrench with force equivalent to the weight of a 10-year-old girl at 72 pounds force. It makes sense. A longer lever requires less force to supply the same amount of torque. Consider this second example scenario. Let's say our motor is producing 8.4 newton meters of torque and is rotating at 1,706 RPM while doing so. Determine the mechanical power output and the real electrical power input if the motor is assumed to be 87% efficient. Our relationship of torque and rotational speed suggests that mechanical power equals torque times rotational speed, and since we're using SI metric system units, we divide this by the constant 9.55, where 9.55, if we recall, is the convenient packaging of the irrational yet constant 2 pi and the 60 seconds per minute conversion. Substituting in the necessary values, we find a mechanical power output of approximately 1.5 kilowatts. Given our previous understanding of efficiency being the ratio of usable output compared to input, we must necessarily supply more input if we are to receive this output. A rearrangement of the efficiency equation suggests our electrical power input equals our mechanical power output divided by efficiency. Substituting in the necessary numbers, we find this motor must consume slightly more than 1.7 kilowatts of electrical power for it to deliver approximately 1.5 kilowatts of mechanical power. It makes sense. Given our previous understanding of efficiency, it always takes more input to deliver a given quantity of usable output because losses will always occur. Staying with this example, what if this motor had a 0.85 lagging power factor? How much apparent power must the electrical utility supply in units of volt amperes if it delivers approximately 1.7 kilowatts of real power to the motor to be converted into 1.5 kilowatts of mechanical power? Our previous understanding of power factor suggests that it is the ratio of real power in units of watts over apparent power in units of volt amperes. Solving for apparent power and substituting in the necessary values, we find the electrical utility must supply approximately 2 kilovolt amperes, so 1.7 kilowatts of real electrical power can be supplied to this motor, which will provide 1.5 kilowatts of mechanical power to our system. Staying with this example for one more round, how much energy will this motor provide, i.e. deliver to a system, if it is used for a period of 1 minute? Additionally, how much energy will this motor provide to a system if it is used for a period of 4 hours? If power is energy per unit time, energy is power times time. If this motor is delivering approximately 1.5 kilowatts of power to this system, it means it is delivering 1.5 kilojoules of energy per second to the system. If it did this for 1 minute, or 60 seconds, the units of seconds would cancel out. It would deliver slightly more than 90 kilojoules of energy to this system over a period of 1 minute. If we use this same motor for a longer time span, it would deliver more energy. In the course of 4 hours, this motor would deliver approximately 1,500 joules of energy per second times 4 hours, where hours must be converted to minutes and minutes converted to seconds. And we're left with approximately 21.6 megajoules of energy having been delivered to the system over the course of 4 hours. It makes sense. When a device of given constant power rating is operated for 4 hours, it delivers substantially more energy to a system than if it was used for 1 minute. Let's say the rotor of a modern horizontal axis wind turbine generator effectively extracts 2 megawatts of mechanical power from the available 5 megawatts in a column of moving air, and the main shaft rotates at 25 RPM. What is the torque supplied to the step-up gearbox by the main shaft rotating at 25 RPM? Given our understanding of mechanical power equals torque times rotational speed divided by 9.55, we can rearrange this to solve for T, where torque equals mechanical power times 9.55 divided by rotational speed. Substituting in the necessary values, we find that the main shaft is delivering 764 kilonewtons of torque to the gearbox. Let's say the gearbox is stepping up the speed 75 times and rotating the output shaft at 1,875 RPM. Assuming the gearbox is 95% efficient, what is the output torque for the gearbox and the input to the generator? Again, efficiency is the ratio of usable output over input, where in this case, input is the 2 megawatts supplied to the gearbox. Rearranging this, power input times efficiency is our output. Substituting in the necessary numbers, we find the gearbox supplies the generator with 1.9 megawatts of mechanical power. Having already observed the output shaft rotating at 1,875 RPM, we can again rearrange the mechanical power formula to solve for torque, where torque equals 9.55 times mechanical power divided by rotational speed. Substituting in the necessary values, we find the high-speed shaft is delivering approximately 9.7 kilonewton meters of torque to the generator. Can you see what the gearbox is doing? It's exchanging the low-speed, high-torque input of the main shaft for the high-speed, low-torque movement of the output shaft. Keep in mind the terms low speed and high torque and high speed and low torque are only relative in nature. 9.7 kilonewton meters of torque is more than enough torque to rip your balls right out of your sockets if you or a piece of your personal protective gear or clothing gets tangled up in the high-speed shaft. It is for this reason shrouds are commonly used to cover rotational mechanical hazards. Additionally, consider where that missing 0.1 megawatts or 100 kilowatts went. It didn't just disappear. It raised the temperature of the oil in the gearbox, contributed to mechanical wear of the gear teeth, and got dissipated as sound and vibration. That's why gearboxes are so big and heavy. They've got to handle the torque, the speed, and the losses. The gearbox stepped up the speed of the main shaft by 75 and reduced torque by approximately 78.9 times. If the gearbox was truly 100% efficient, these values would have been equal. However, due to inefficiencies, we've lost some torque in the gearbox and are delivering only 1.9 megawatts of mechanical power to the high-speed output shaft of the available 2 megawatts supplied by the main shaft. The gearbox in this case is exchanging torque for speed so the turbine can generate at a frequency consistent with that of the grid. Regarding the efficiency of this whole turbine, one might be shocked to notice of the available 5 megawatts in a column of moving air, the rotor only extracted 2 megawatts of it. And because of inefficiencies in the gearbox, the high-speed shaft is only delivering 1.9 megawatts to the generator. If we keep moving down the line, a reducing quantity of power is made available as useful input as each stage extracts its toll of efficiency losses. Let's say once output clears the generator, any power electronics in the converter, and the transformer, only 1.5 megawatts hits the grid. We can therefore say this turbine is only 30% efficient. This 30% efficiency figure is something the gullible jerks of the world are quick to seize upon as evidence of wind power's inefficiencies. Hold on now. What happened to that spilled 3.5 megawatts of wind? Who cares? There are limits imposed by hard physics. The Betz limit says you can't capture all the power in the wind, otherwise it wouldn't be windy. The real thrust of it is this. Did you have to pay for the wind? No. Wind is limitless, wind is cheap, and you don't have to prop up amoral dictatorships in some hellhole halfway across the world to ensure the wind keeps blowing. That's the point of renewable energy. The fuel is free. Yes, you have to purchase, install, and maintain a wind turbine generator as you would a fossil fuel power plant. And yes, balancing intermittent distributed sources will be far more complicated than traditional centralized generation. But when the wind blows, the river runs, or the sun shines, as they are regularly known to do, the fuel quite literally falls from the sky. All you gotta do is catch it. Who cares if you spill an armload if your planet is continually bathed in free fuel? Now that we've got an understanding of the general concepts of torque and rotational speed and how they relate to mechanical power and energy, let's apply these concepts to a discussion of motors. Here is a speed-torque curve for a generic three-phase squirrel cage induction motor. In this case, the profile is meant to represent a NEMA design letter B. We can see it has different torque values at different speeds that are related to its synchronous speed. Your two most immediate questions might be, what is a three-phase squirrel cage induction motor and what is synchronous speed? Don't worry about it right now. Just realize each motor has different speed-torque characteristics, and this graph is a handy means of exposing you to these concepts right up front. The more exposure you have now, it'll be easier to understand when we go into nauseating detail later. For now, let's just look at the shape of the curve and notice some interesting points on it. Basics first. The horizontal axis is speed. The vertical axis is torque. To read the torque at a specific speed, just walk along the speed axis until you hit that speed of interest. Then walk up till you hit the torque curve. Read the torque on the vertical axis. The first point of interest is our synchronous speed, which is a function of AC excitation frequency and the number of pole pairs per AC phase. Again, don't worry about all the $10 words right now. We'll discuss synchronous speed in the rotating magnetic fields lecture. The only thing we're concerned about right now is mechanical power, speed, and torque values. Be aware that sometimes you'll see the horizontal axis expressed not in units of RPM, but rather as a percentage of synchronous speed, where synchronous speed is obviously 100% of synchronous speed. The same thing with torque expressed as a percentage of full load torque. Just under the synchronous speed is the no load speed, i.e. the speed at which this motor spins freely when there's nothing to counter its spin. This is a point where speed, N, is pretty high, but torque, T, is 0. Notice in the case of a three-phase squirrel cage induction motor, its no-load speed is just under the synchronous speed, meaning even if it's unloaded, the rotor is ever so slightly lagging behind the rotating magnetic field produced by the stator. As we'll learn in later lectures, there must be a lag or slip behind synchronous speed for a squirrel cage induction motor to work at all. At the other end of the curve is the locked rotor torque, sometimes called the starting torque, a point where torque is respectfully high, but speed is 0. My question to you about both these points is, what is the mechanical power exerted by this motor? It is not a trick question, it requires little to no math, and honestly, doesn't even require an understanding of any of the subject matter we've thus far dealt with in this lecture. All it requires is an understanding of power. Let me rephrase this question ever so slightly and break it into two parts. In the no-load conditions, what is the mechanical power when it's going really fast but delivering no torque? In locked rotor conditions, what is the mechanical power when it's really strong but going nowhere? The answer in both cases is 0 watts. Prove this to yourself with the formula mechanical power equals torque times rotational speed divided by 9.55. Let's say at no load conditions, torque is 0 and rotational speed is 1,760 RPM. And in locked rotor conditions, it's exerting 1.8 Newton meters of torque, but at an absolute standstill. In no load conditions, it's delivering 0 watts of power. In locked rotor conditions, it's delivering 0 watts of power. If I was to plot mechanical power on the same vertical axis, in between these 2 points of 0 watts is where things get very interesting. Take this point right here. This is the full load conditions, characterized by a rated speed and rated torque. This is some of the pertinent data you would find at a motor nameplate, which we'll discuss in the motor nameplate information lecture. At these conditions and these conditions only is where a motor would draw its rated current given it's supplied with rated voltage. It's really just a region of this linear slope right here where torque and speed kind of play nice and behave as one would expect. If you load up a squirrel cage induction motor, it slows down. If you unload it, it speeds up. Load it up too much, however, and you enter this breakdown region, the major transition point being the breakdown torque, the maximum torque this motor can produce. This is kind of where the motor stalls out and there's this diminishing return on mechanical output. If one was to calculate and plot mechanical power at all points along the speed-torque curve, you would plot a power curve on the same axis with this second vertical scale representing watts. If at locked rotor conditions and no load conditions both deliver 0 watts of mechanical power, and the motor is obviously doing something between these two 0-watt conditions, it stands to conjecture there exists some region of maximum positive mechanical output. We'll get to polarity housekeeping in a bit here. The region of maximum power might exist within this linear region, not necessarily at full load torque and rated speed conditions, but somewhere in the neighborhood. If we overlay this general power curve, it might look something like this ugly approximation in orange. In addition to avoiding a stalled motor beyond breakdown torque, we're obviously operating in the linear region of the speed-torque curve for a reason. Not only is speed and torque related relatively linearly, we're trying to stay in this sweet spot in the power curve where mechanical power output is pretty high. Let's say there's a point on this speed-torque curve where the motor is spinning at 1,550 RPM, producing 2 Newton meters of torque. What is the mechanical power output in watts? Before you pull out your abacus, let's lay some ground rules regarding polarity and housekeeping using signs. These ground rules are very basic, but very important because I tie directly into the whole concept of motors and generators being dual aspects of the same electrical machine. The only reason I'm doing this is because we're discussing both aspects of the same machine at the same time, and we need a quick means of distinguishing between something consuming electrical power and producing mechanical output, a motor, and something consuming mechanical power and producing electrical output, a generator. Take, for example, a motor exerting a certain amount of torque against an opposition torque. The point is, the motor torque and the opposition torque are exactly that, opposing, meaning of equal magnitude but opposite sign. The real-world applications of motors sometimes use a gear set to drive a load. Picture a drive gear on an output shaft that spins a driven gear. An example might be a yaw motor on a horizontal axis wind turbine, which actively turns the wind turbine into or away from the wind. The motor is mounted to the nacelle frame, and as the pinion or drive gear on the motor shaft spins, it rotates the frame on an externally or internally toothed slewing bearing, which is fixed to the tower. Another example of this on a wind turbine is the pitch mechanism that changes the angles of the blade using a motor with a pinion gear driving an internally toothed slewing bearing. As the motor spins the pinion, the blade changes the angle of attack. Both of these applications, because of the gear set, change not only the speed and torque characteristics of the mechanism, but sometimes the direction. Even if you have no understanding of gear ratios and gear sets, you should at least understand if I spin the drive gear in one direction, the driven gear spins the opposite direction if it was externally toothed. Despite the real-world practical application of this setup, it adds a serious complication to our earlier discussion of signs and polarity, which, if we remember correctly, was supposed to make things easier in the first place. This is to say nothing of either gears and multi-stage parallel gear sets and planetary arrangements. So let's use this setup instead. A motor with a chain drive, turning a load with the exact same size gear. When the motor spins the shaft clockwise 1 revolution, the load turns 1 revolution in the exact same direction. There is no step up or step down or direction change or anything else to complicate our discussion. Think of the chain drive on your bike without the change in gear size. Every 1 crank forward turns the wheel forward 1 rotation. Another example is a pulley and belt system in one of those old school garment factories where all the underage workers are always getting their arms cut off by pulleys and belts. The motor doesn't know it's actually hooked up to some crazy gear set or pulley. All it knows is that something is opposing its output. Let's get right to the point about polarity. If a motor spins in the clockwise direction, it produces clockwise torque. The opposition torque is counterclockwise. If a motor spins in the counterclockwise direction, it produces counterclockwise torque. The opposition torque is clockwise. In both occasions, however, we've got to say that this motor is producing positive mechanical output. How can we use a polarity convention to make this a reality when 2 different directions produce positive mechanical output? One could flip a coin and simply declare one direction positive and the other negative. And I'm far more comfortable with my role as a benevolent tyrant with absolute authority than blind chance. So I hereby declare henceforth that clockwise rotational speed and torque shall now and forever be known as positive, and counterclockwise rotational speed and torque be known as negative. Let it be written, let it be done. Woe to those that disobey this royal decree. Returning to our example problem before we took this lengthy detour is a case where a motor is spinning at 1,550 RPM clockwise and producing 2 Newton meters of torque clockwise. What is the polarity of both values? Speed, because it's clockwise, is obviously positive 1,550 RPM. Torque produced by the motor is in the same direction as its rotational speed. Therefore, it is also positive. The opposition torque is negative 2 Newton meters, but I am not concerned about that. The motor is producing positive 2 Newton meters of torque in the clockwise or positive direction. Most importantly, the torque produced by a motor, regardless of its direction of rotation, is in the same direction as that which it is rotating. In motor mode, torque and speed are in the same direction. This obviously excludes special circumstances when a motor is being plugged to brake it or fighting another motor. For our example problem, mechanical power is equal to speed times torque divided by 9.55. Substituting in the necessary values, taking into account polarity, we're left with approximately positive 324.6 watts. Positive speed, positive torque, positive mechanical power output. Let's try a second example where this motor is reversed and spinning counterclockwise at 1,620 RPM and producing 1.59 Newton meters of torque counterclockwise. Using our polarity convention, given this is counterclockwise rotation, we could say both our rotational speed and torque is negative. Substituting these numbers into our mechanical power equation, negative times negative equals positive, and we find this motor is delivering roughly positive 269.7 watts. If this seems like a complicated shell game for this level of difficulty, I'll kind of admit it is. Be aware, however, this polarity convention comes in extremely handy and is important, oh so important, when it comes to discussing the mirror image of the motor, the generator. Thus far, we've spent a lot of time using the relationship of power in always equals power out, where power in the case of a motor is defined as the real electrical power input to the system, and power output is defined as the mechanical power output of the system plus losses. It would be a terrible shame to suddenly abandon this definition and confuse everyone. You'll see by using a polarity convention, it's very easy to continue using the same definition from the perspective of a generator, which exports electrical power when it has mechanical power input to it. In this case, I'm neglecting losses and assuming 100% efficiency to keep our analysis simple. If positive electrical power is input to a motor and it supplies positive mechanical output, what would happen if a generator was exporting electrical power and we wanted to keep electrical values on the left-hand side of our equation and mechanical values on the right-hand side of the equation? Sounds like a simple switch of signs could take care of this. We're left with a relationship with a negative sign on both sides of the equation. Although it is a mathematically valid technique, don't be tempted to remove the negative sign because it's an extremely useful indicator of polarity and direction, as we'll find out in a moment. Positive electrical power input means a motor is consuming electrical power. Negative electrical power input means a generator is exporting electrical power. Positive mechanical power output means a motor is delivering mechanical power. Negative mechanical power output means a generator is consuming mechanical power. Returning to an expanded speed-torque curve from our earlier motor examples, you'll realize I previously only gave you a small portion of the curve, that where torque was considered to be positive. If we consider only a case where things are rotating in the clockwise direction, what would happen if an outside force, let's say falling water, moving wind, or expanding steam, was to grab the rotor of a three-phase squirrel cage induction machine and spin it faster than synchronous speed? You would find this extended speed torque curve that looked like this. For those of you that have been following my discussion of polarity regarding mechanical power, you'll you'll find immediate satisfaction in keeping those negative signs where they were in the first place. For those of you that are hopelessly lost, just rewind a minute or two and get that concept down before you continue. What is readily apparent from our extended speed-torque curve is that there is a region above synchronous speed, i.e. when the rotor is spinning faster than the rotating magnetic field or the electrical machine, because above the speed I can no longer truthfully call it a motor, is resisting my movement by supplying negative mechanical power. Don't believe me? Verify this with a simple application of our mechanical power equation, taking into account polarity. Mechanical power is equal to torque times speed divided by 9.55. If we had a positive speed and a negative torque, this would mean negative mechanical power. Let's take this point right here, where the rotor is rotating at 1,910 RPM in the clockwise or positive direction. However, torque is a negative value of negative 1.5 Newton meters because it is counterclockwise in opposition to the direction of rotation. You get it? Substituting in the necessary values taking into account polarity, positive times negative yields a mechanical power output of negative 300 watts, meaning that the shaft is resisting whatever outside source is attempting to spin it faster than the rotating magnetic field in the stator. If this device was truly 100% efficient and power in always equals power out, we could also say that this device is consuming negative 300 watts of real electrical power. This means it is exporting electrical power. Let's get right to the point about polarity regarding generators. If an outside force like falling water, moving wind, or expanding steam was to spin the rotor of a squirrel cage induction motor at a speed above synchronous speed in the positive or clockwise direction, that outside force has to overcome an opposition torque opposite to the direction of rotation. Positive rotational speed, negative torque, negative mechanical power. If this device was hooked up such that the rotating magnetic field was rotating counterclockwise, and that same outside force also switched direction and started spinning the device at a speed above synchronous speed in the counterclockwise or negative direction, it would also have to overcome an opposition torque opposite to the direction of rotation. Negative rotational speed, positive torque, negative mechanical power. In both cases, positive rotation or negative rotation for a region above synchronous speed, torque exerted by a generator is opposite to the direction of rotation. Can you now dig regenerative braking on the same level that I do? In summary, here's how both aspects of an electrical machine work using our new polarity convention. In generator mode above synchronous speed, torque is in the opposite direction as rotation and produces negative mechanical power output and negative electrical power input. In motor mode below synchronous speed, torque is in the same direction as rotation and produces positive mechanical power output and consumes positive electrical power input. You may not find this clockwise, counterclockwise convention universally applied because my royal jurisdiction only extends so far. However, if you can understand the fact that motors exert torque in the same direction as rotation, and generators oppose movement by exerting torque in the direction opposite of rotation, you'll do just fine. Sticking with this polarity convention, though, makes it easier to keep your house clean and figure out who is doing what. Bring our discussion of mechanical power, torque, and speed to a close with a quick look at common instrumentation used to measure torque and speed of rotating electrical machines, namely a dynamometer and a tachometer. Since no one on earth can spell these words, most folks refer to them as a dyno or a tach. Even if you don't walk away from this lecture fully understanding mechanical power, torque, and speed, you'll walk away sounding like you do if you use these cool slang terms. A dynamometer measures torque, and a tachometer measures rotational speed. The product of these two, then divided by 9.55, is mechanical power. If you measure the amount of seconds one is delivering or consuming power, and multiply that time by power, you get energy in joules. Sounds familiar? 4 results from 3 easily measured pieces of data: torque, speed, and time. The dynamometer is especially neat because there are actually 3 general types. The first one is an absorption dyno, which if you think about it, is kind of like a punching bag for a motor. It can load up a motor by increasing opposition torque and measuring the torque exerted by the motor to balance this opposition torque and display it on a meter. Old school examples of this type might be a frictional wheel or a prony brake. A drive dyno is the exact opposite. It produces torque to drive an electrical machine, and it'll display the opposition torque that the electrical machine is exerting against it. It's kind of like a prime mover. The third type is a universal dyno, which is a combination absorption and drive dyno. Such a device is useful in a lab setting to discuss the dual aspects of motor and generators. There are several methods of measuring speed, but they all fall into two general categories: contact and non-contact tachometers. Contact tachometers are sometimes called tachometer generators, and they obviously physically contact the device they're supposed to measure. They produce an analog output voltage proportional to RPM. The output RPM can be read on a needle meter or input to a computer and digitized for later processing. Non-contact methods of rotational speed measurement are numerous. A handheld laser tachometer can be used to measure the speed of a rotating mechanical object. In this case, a hydraulic motor. This is a retroreflective laser tach because it requires a piece of glint tape on the motor shaft to return the transmitted laser light back to the receiver. This is obviously not the preferred method for measuring a shiny metal object. In that case, you might need to use a polarized retroreflective scanner. The laser tach can't be held too close nor too far away if you want accurate results. Resist the temptation of shining a laser tach in your or your lab partner's eyes. This is what it looks like without all the searing pain and inconvenient blindness. I'm doing so because there's a camera and a whole lot of internet between this laser and your eyes. Consider your curiosity satisfied. You don't need to pay some unschooled youth $8 an hour to sit there with a laser tach to get valid rotational speed readings, because there are numerous automated methods of doing so, all falling under the blanket term Rotary Encoders. If all we're concerned about is rotational speed and not direction or position, a single Hall effect sensor on a shaft is more than sufficient to do so. Every time an indicator, the presence or absence of a metal object, passes through a Hall effect sensor, it detects that presence or absence and indicates it with a pulse, hence the term pulsar. If a single indicator on a shaft passes a sensor 30 times in 1 second, this means the shaft is traveling at 1,800 RPM. The single sensor scheme has a disadvantage though, because you cannot tell which direction the pulses are coming from. A single clockwise rotation produces the same amount of pulses as a single counterclockwise rotation. This can be overcome with two sensors with a slight angular offset between them. Tag A is in front of tag B. If these two sensors are in line with one another, and the shaft is rotated in this direction, sensor A will receive a signal before sensor B. If the shaft is rotated in this direction, sensor B will receive a signal before sensor A. The time it takes between subsequent signals at each sensor is indicative of speed. For example, if sensor A received a pulse every 50 milliseconds, it means the shaft is revolving once every 50 milliseconds, or 20 revolutions per second. If we stood there for a minute, we'd see the shaft revolve 1,200 times. The order in which the sensors receive input is indicative of direction. If sensor A is receiving the signal first, we can be assured that the shaft is revolving in this direction. There are varying levels of complexity of this type of rotational speed measurement, and it is sometimes referred quite surprisingly as A-B encoding, incremental encoding, and/or quadrature encoding. We'll get to these methods in much later lectures. Much later, we might visit absolute encoding, in which each angular position on the shaft is assigned a specific binary combination, utilizing something called gray code, where only one bit position changes for each transition to the next position. For now, just think of these advanced methods as super fancy means of determining not only rotational speed and direction, but also relative or exact position of a shaft. In conclusion, this lecture presented important terminology used in discussing basic electrical machines operating in motor or generator mode, namely torque, speed, mechanical power, and energy. We discussed torque and speed polarity and how this shell game helps you keep track of whether a machine is consuming electrical power and outputting mechanical power in motor mode, or consuming mechanical power and outputting electrical power in generator mode. Finally, we discuss common instrumentation to measure torque and rotational speed, like the dyno and the tach, as well as automated means of doing so. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.